This is a short video presentation to solution to question 3.16 from the FEEG1003 Thermofluids workbook. So here's the question. It's a standard nice short question. Got some variables in there. So the first thing you need to do when solving any of these engineering type problems is to read the question really carefully and underline all the important things that we think we need to use. So I'm just going to highlight all of the variables that we've been given. So it's an ideal gas question. We've got some properties of state here. So we've got initial pressure and volume, and we've also got a final pressure. Right, next I'm going to do is underline all the key parts. So all the key words and everything like that. So that we've got gas, it expands. That's really important. Okay, our initial state P1 V1 to a final state P2, and here we go. The relationship between pressure and volume during the process is PV equals a constant. Right. So from that statement we already know that if P1 is 500 kilopascals, V1 is 0.1 meters cubed, then the final volume must be 0.5 meters cubed, because P times V is a constant. We have P1 and V1, so we can work out the relationship between P2 and V2. Right, so we've solved a bit already. Sketch the process on a PV diagram. So we've got to draw the process on PV diagram and determine the work. So the work in kilojoules. Okay, so this is the amount of energy. Right, if we draw a quick diagram of this, not PV diagram to start with, we'll just do a sort of a schematic, very bad. So we'll assume the gas is in some sort of vessel. I'm going to be lazy now and just draw a piston. Okay. Trying to write and draw with a mouse is incredibly difficult. Okay, so here's our gas. Oops. And we know it expands. So this piston head's going to move in that direction. So the gas we're going to assume is a closed system, and we know it's expanding, and PV equals a constant, so it's a polytropic process. Right, we can move to the whiteboard now to solve this. So we need to draw, next thing to do is draw a PV diagram and determine the work. So drawing the PV diagram will help, but determine the work, that's the methodology part of the question. This is the part of the question where we've set it up. We've got our start and end variables, properties of state, P1, V1, P2. We know what V2 is because we read the question carefully. Now we need to determine the amount of work done. We know the gas is expanding, so it's positive with work done by the gas on its surroundings. I know that because I already know a little bit about ideal gas. And also you will need to know how to determine the work based on a process drawn on a pressure volume diagram. Okay, and just to give you the answer straight away, it's going to be the area underneath that process line. Okay, so you need to know that. The next part of the methodology is going to be how to actually work out the area under that process, and for that we're going to have to use some fairly entry-level maths. Okay, so I'll move over to the whiteboard now and just quickly finish off this question. Right, so I've drawn a PV diagram and I've labelled the axes. So we'll put our start and end state. We know the property of state at point 1, we're told in the question. Here. And then because PV equals a constant, and we knew P2, we know our end state, which is down here. Okay, these are our two properties of state, and we can draw a line between them. That's the process line. And finally, it's always very important to put the direction of the process. Okay, going that way. Right, so to determine the work, we need to find the area under this process line. So that's equal to the integral of this. Okay, so the integral, our limits are V2 and V1, and it's the integral of P times dV. We can make a substitution for P, so we know that PV equals a constant, so P equals a constant over V. Okay, and then we can solve this integral. Okay, so it's equal to the work done equals P1 V1 multiplied by the natural log V2 over V1. So just quickly working that out. So we've got 500 kilopascals times V1, which is 0.1 times the natural log of 5. Okay, and that gives you the answer in the book, which is 80.5 kilojoules of positive work. We just get rid of that 10 to the 3, then we're all happy that we've calculated the answer in terms of kilojoules. All I did was make this into joules and meters cubed, just to keep it all in SI units. The answer is positive because it's positive work that's being done. The gas is expanding, so it's doing work on its surroundings or work on something else. Okay, so in terms of the methodology, we set the question up already, and then the final bit is obviously knowing that in order to calculate the work done in pressure volume space, we need to know the area underneath the process in question. And for that, we need to integrate this expression. So this is where the maths comes in, and that's the final part of the solution. Be careful with the numbers, and we get the correct answer out. All done.